Good morning. Good morning, everyone.
Good morning.
How are you?
Good morning. We are fine, and you?
I'm good.
Good morning, everyone.
Good morning.
I have an issue. My ENSP is still having issues. The error code of 40 has refused to go off. I've done everything. I've even tried installing a desktop, the same error. What could be the problem?
Okay, from my experience, usually one error 40. Okay, one thing I know is, okay, there is Windows. You can first cross-check Windows. Like if you do update your computer Windows to the latest, it will not support the old ENSPs. It will say this is not compatible, so it will want you to download the updated ENSP. It prevents that one. But if your Windows is not updated, second would be your computer RAM. And when you're running, error 40. Yeah. Just a minute. So which ENSP version are you using?
The one Alex sent to us. I think it's version. I think it's 1 point. I think 1 point something. It's 1 point. Let me just check the version. It is 1.0, I think.
There is one
version 3 or version 1. Okay.
It must be version 1, because when you go to all programs, it is version 1.
And you say the error code is what? 41 or 40?
Error code is 40. It can't start the device. It can't start. It can't start the routers. The version is 1.3 for the ENSP.
But according to me, I think this error is coming from the virtual box.
Yeah, that is true.
Which it will require a higher version. Yeah, the ENSP or installing requires at least 5 point in the virtual box branch 5.0 and above.
Morning, everyone.
So, have you tried doing any labs yet so far?
Yeah, okay. If I change the router to the real router, it works. But when I try to configure with the one that comes with the exercise, it doesn't work.
Usually, did you register your devices like after installing ENSP?
That is very true.
You did register, right? Okay.
I registered the devices.
Okay, last time John did talk about that error 40 comes when the ENSP fails to get load like the router images from the virtual box. It fails to pick them up. You get? So usually when I get error 40, you can troubleshoot, but it takes a longer time. I don't know, like you have to check, probably sometimes you will have to delete the images from ENSP, then you reinstall them again. But what I usually do is I just reinstall the whole thing and reinstall it again. Did you do like installation of virtual boxes and all that? Did you install them independently or like you install the whole package? because
No,
there is that
it's not.
version. Pardon?
Okay, you are saying there's that version. You first complete, then maybe I can tell
There
you.
is that, yeah, there is that version 510 that ends with 510 that is in the channel. When you're installing it, it automatically it will install for you the win pickup and the compatible virtual boxes, so you won't have issues with it. You get?
Yeah.
Yeah, I always find
I install them independently. Yeah?
That
one by
virtual box,
one.
the virtual box in that.
Would
Jonathan,
that be the issue?
Jonathan,
Yes.
what I did for my case, sorry, I disconnected. What I did for my case was I updated my virtual box. That error 40 was solved by updating my virtual box.
By
Both
updating
Windows, yeah, I updated my virtual box because the one that is coming with the NSP was a lower version compared to the Windows version that I'm using. So I don't know Boniface is using which kind of which version of Windows is he using?
I'm using Windows 10, but which version it will update to, like, for VirtualBox? Because there are different versions of VirtualBox.
If are you using Windows 10 or
Yeah,
Windows?
maybe I will try that version you upgraded to, so that I can also. I use 10.
You use Windows 10
Yes.
version 20H2 or which version 1903?
Yeah, that one.
20H2.
Version 20H. Yeah.
Jonathan,
yes.
okay, my name is Richard. I still have an issue with my zipped folders. After configuring my topology, everything, saving, after zipping the file, when I review it, I find that the configurations are gone. What could be the problem? But last time I talked to John and sent him the zipped file, he said everything was okay.
Boss. Boss.
Yes.
How the guy with the issue of the zip, how are you zipping the folder?
Okay, I am using that. I highlight the folder, then I click send to. Then I choose the zipped folder.
Now listen,
option.
when you open it, after zipping your folder and you open it to check it, whether the configurations are there. How do you open? You just double click or you extract?
Okay, I should extract.
You should extract. If you double click it, you will get that problem. But if you extract, everything will be there.
Boniface.
Thank you. Let me try.
Okay.
Yes, please.
Boniface, I've just shared the VirtualBox version that I'm using. If your Windows is 20H2,
Which version have you used?
Just check the charts. Check the charts.
Okay.
I've just posted
Fine,
it.
fine.
Yeah,
Okay,
just
thank you.
like that.
Let me check it.
And ensure that you register the images. First, delete the ones that were there initially, and then you register fresh.
Okay, let me check it, and then I'll try that. Thank you.
Okay, Jonathan.
Guys, is this gentleman complaining that he has an issue with 20H2? I would advise him to do the following. I'm going to upload a SIP ENSP setup that has worked for me flawlessly. However, you will have to start with installing the Wireshark first, then install the ENSP. I'm actually going to post it on the Telegram group because since I started using it, I've never gotten that error code for it. So I hope that will help him.
Yeah, that's fine.
Jonathan.
Yeah.
Yeah.
Actually, you can ask. Yeah.
I'm requesting anyone, not even if Jonathan. I'm just requesting support in terms of floating static route. I just configured it, but I did it the other way around. It worked, but now from the way the exercise is required, it's not working.
Which lab is that?
Lab 7.
Let me just have a look at it. You did so on branch biz network, you did configure static route too, right?
I did configure static route from route 1 to route 3.
Hello, how do you configure static routing? I tried configuring static routing, but
IP static. It's IP static route.
What's wrong with you?
Then you put your destination, then mask. Then you put the IP of the other end route.
the destination, maybe I'm confusing the destination and the mask and the what is which one is the destination? For example, on lab 6, we have router A and router B. Then router A, it's 192.168.10.1/24. Then router B is 192.168.10.2/24. Which one is the destination? Which one is the
Right, how you determine the destination depends on which network you want to access. So if you're from router A, for example, you want to go to router B. Now router B network, that is the first destination. That's your destination. Then you need to specify the subnet mask of that destination. Then from your router, that is router A to router B, at what interface are you getting into that network? That is now the last point. So actually, how it will be now IP route static. Your destination is a network B or router B. The IP address, then subnet mask. Now from router A, what is the interface through router B? The IP address.
From router A to router B, the interface, which one is the interface here?
Now the I've not mastered your IP address that you listed. Let's say from router A to router B, the first interface from router A to router B, let's say it's 10.1.1.2. And then I wish we had some diagram because now you're stretching it. These are, I don't know if you really understand it.
Maybe he can share his screen probably in case. I don't know if he has, if the admin gave right.
Okay, just a while.
Try sharing your screen. I think sharing screen has been disabled. You can't share your screen as of now.
Oh, sorry. I was just trying to test if you can share. This is the lab you're talking about, right?
Yeah, this is now lab 6. I think that's what you wanted. You can illustrate from there.
Right. So he wanted how to configure static routes.
Yeah, how to configure static route and which IP do you use? I think you can scroll down. Just scroll up.
No, actually, they're here. These are the ones, right?
Yeah. So
Maybe.
what you want?
Yes.
What you wanted to know is the destination network and the interface. Now the interface from router A, I hope you're seeing the interface from router A to router B. At what point is it going into the other network? That is, it will be now 192.168.10.2. I hope you're seeing that. Gigabit Ethernet. Are you seeing Ethernet
Just a minute.
000?
This. So just let me see if these pieces are configured. Like, can we do this just, I don't know how fast we could do this together probably.
Let's do that. But also have that.
Yeah, you can do it.
So you give this router, you give it IP and this is the gateway. So oh, someone did ask how they save commands on PC. There is always this apply button.
Yes.
Someone called Mugujit, please mute yourself.
Okay.
Yeah, 255.0. Then you give it the gateway is 10.0.1.254. .254. So I'm going to first configure only for one PC here, so that let me see 10.0.2.4 with a subnet of 255.255.255.0 and a gateway of 0.2.254. So when you give this, so I'm going to configure that router. I hope so you can see this, right?
Yes.
Yeah, so I'm going to configure these interfaces. You go to system view, just enter, then router A, then you give it IP addresses. So on this interface 1, that is its gate. So you go to that interface, that is gigabit 001, and then I give it an IP address can use, these are just abbreviations, but it's IP address. You give it 10.1.0.254/24, and you go to interface 0, and you give it an IP of 192.168.10.1/24. And if you can see display IP interface brief, you'll see that on 0 and 1, your IP addresses are allocated. And if I go for this router B,
Okay. Wait a bit.
yes,
Gigabits Ethernet 000. We get it the gateway, the default gateway, the IP address of that.
0 here, you can see here, this is here, right? Then
Yes.
this one, it's this one, 254. Yes?
Okay, there are new addresses you give. It's new addresses besides those given there.
Pardon?
192.
You can continue.
Okay.
Excuse me, does it matter the arrangement?
Like, what do you mean by arrangement?
Okay, like the one which you have started with, instead of that, you start with the second one. The one
No,
you came with last.
No, it doesn't. You can start with this one. You can start with, like here, you can say I started using what? I started with interface 1. Yeah, 1
No,
0.
I think what is meaning, because if you put, instead of putting on 1 and you configure on 2, it will not communicate. I think that's what is meaning. He wants to ask, does it mean like you put for interface 1, you put the first one, or you put the second one? I think that's what is meaning. It's not.
So the order doesn't matter. Whether you configure this one first or this one the second doesn't matter. Then the second is you have to follow your topology. So where you seeing gigabit 001, you give it that exact.
I think that's what it means. That's what
you
it's
give
meaning.
it that. You give it that exact. Also for gigabit 00, you give it this IP address here.
Oh, in other words,
yeah, that's what he was asking.
Yes, so if I interchange, it will not communicate.
Yeah,
no,
there were people who were having challenges in previous labs was because they will probably disconnect this router, and then they will connect your interface gigabit 3, and they still give them this same IP address. Then, yet on the routing table, you're having this. When you check when you run IP routing table, it will put for you physically down. You know those things. So you follow your diagram. Where there is 1, you give it that. If here was 2, you also give it, instead you will give that IP address you get.
I think that's why it is fading here.
Okay, Jonathan, can you please continue? Continue with the router B.
Okay.
Jonathan, just a moment. Jonathan.
Yes.
A moment. Now, if I want to erase all the data on router A, which command do I run?
You just undo the command you did run. Like here, like for interface 2, if I did want to remove that IP address, I'll go to interface this.
Okay.
Then I just run undo. This command, you see this command that you typed, where is it? It is IP add, this one.
Yes.
You just copy that, and that same command, you just paste it there. You can see from that, when I do that and I click enter, then I do display that IP will not be there. It has been removed.
Okay. Okay, right.
Yes.
Jonathan, what if one wants to delete the whole configuration on a particular router?
You want to delete the whole thing?
Yes.
You can just add it manually, like just a minute. If you can't undo, then probably what you can do is, in case you have not saved, in case you have not run the saved command, you can,
Okay, you complete, then I will ask you later.
Maybe can we continue, then we come with questions?
Yeah, we shall ask the questions at the end. Let us continue.
Yeah, because our time we're only given 1
Our-
hour. So
Yes.
on router B, then I give this interface gigabit 0, that IP address. So I go to interface gigabit 00, and I give it that IP of 192.168.10.2/24, like that. Then I go to interface 2, and I give it an IP of 10.0.2.254/24. You can always verify your answers by just running display IP int to see. In case you have challenges with communicating, you can just always run this command to see if you've allocated the IP addresses correct. So it will display for 1. Yes.
I have a suggestion.
Yes.
As we are continuing, do you think we can add another router so that as we will be implementing static route, we can also implement the floating route? Because the time I can see we are all remaining in less than 20 minutes, so that we do one at a
Jonathan,
time.
first complete this. First complete this.
Jonathan.
Because the problem with the static routes.
I think let's make it easy. Who is having the exact problem with static routes?
It is
me.
It is me.
And me too.
Now, when you say me,
Apollo.
Francis.
Right.
Jonathan.
Yes.
I think. Okay. Static route. Which lab?
Lab 6.
Lab 6.
And 7.
Is lab 6 the first one we had static routes in?
Lab 6.
Yes.
One, yeah.
Because I don't want us to do for them work.
Yes.
You get the idea?
Yes.
If we go through this lab like this, we are doing for them work.
John, my suggestion.
Excuse me.
My suggestion was.
Yes.
I was suggesting
Like this.
that. I was suggesting for us to understand this static or floating static route, we can just draw a different topology to get to understand it than doing it doing the lab exercises.
Yes, that's the idea. I don't want to do for you work.
Jonathan, a quick one. A very quick one.
Yes, John.
Yes.
Yes, the reason why actually it would be better if it's doing one, not exactly the lab exercise, but at least it can help us know our mistakes. Now, for example, I did know that maybe if you interchange the interfaces and the IP address, it can stop it from communicating. But at least now I do know that, and I don't think that.
But
will be
why
an
do
issue
you
again.
interchange IP addresses when IP addresses have been shown in the topology?
So I did not know that.
No, but if you're told get into room number 7, why do you go to room number 15? Do you need to first know that it has to be room number 7? Because they would have told you room number 15. Are we together, guys?
Yes, what I'm saying, the interface.
Let us handle real problems.
Okay, a quick one.
If they tell you to configure IP address 192.168.10.2 and you make it .10.7 because you think even .7 will work, there is a reason you were told .2. Now that is not a problem.
I'm not saying that. I'm saying, for example, this one here, the IP address of 10.0.1.254, it corresponds with the interface 1 of router A. But now I had interchanged it to whereby I was putting IP address, that IP address on interface 0. So that's why it was not responding, but everything was done right. But at least from his explanation, I've understood that maybe, yeah, that was my issue there.
John.
Because you know why I want to become hold a sec. Jonah, sorry, interfering, but you know, in my experience, we might end up spending the whole day and we shall have exactly the same questions in the next lab.
No,
Okay,
like
so let's finish up. Let's finish up.
a quick one.
Yes,
A very
that's
quick
true.
one.
Time. We have no time.
My ENSP is telling me I'm on lab 7 that too many devices will lead to lack of memory. Please reduce the number of devices. How can I solve that?
Increase the RAM.
Just that.
Because it is telling you lack of memory. You know,
Mr.
like,
John.
seriously, when you reach P6 and they tell you, when you reach P6 and they tell you your brain is small, you won't proceed to P7, you do what? You stop schooling, you can't increase your brain.
That's
John,
the issue.
I think he should.
I think
start a
from my
few of the devices
experience,
at a
that used
time.
to happen if you have some devices that are not connected. So if you have some devices that are not connected on your interface, kindly remove them from the screen, okay? And go on with your configuration.
Yes. Well, my answer is assuming that you're configuring a topology we gave you, and then that topology means it is only the devices in the topology running.
But if I have a RAM of 8 GB, then how much RAM do I
Now,
need?
if you have a RAM of 8 GB, it means you're probably having a lot of other programs running or something like that. Or try starting the devices one by one.
Okay.
My problem is timeout, John. When I ping, I get timeout only.
You do what?
When I ping, my problem, when I ping, I only get timeout.
By timeout, what do you mean?
That means the network you are trying to reach is not reachable. If it's unreachable, then that means the network the address you are trying to reach is within the network, but it's not connected to a particular PC. But if it is timeout, it is on another network that is unreachable. So probably you need a routing device that will route your information from one network to another. So then you overcome the issue of timeouts.
Okay.
So you guys can see my thing here.
Yes.
Yes. This is what I want to know.
You think it won't get finished? It will get finished. Then you'll start saying this is what you want to know when it is something different. Yeah, I'm hearing some particular one person insisting, for me, this is my problem. This is, we shall do it. And then you start saying, no, this is my problem. It is something different.
John, sincerely, the problem was configuring static routes. I've been stuck on lab 6 for 3 days.
No problem. Is this not what I'm doing here?
Yeah.
Yes. After that, I'm going to send you KFC.
Now I'm excited.
I'm connecting interface 10 of the switch to interface 2 of the router, interface 0 of the router to interface 10 of the switch. Let me turn on these interfaces.
And the popcorn.
So this is the topology. This is 2. This is 1. This is switch 1. This is gigabit Ethernet 2. This is gigabit Ethernet 0. This is gigabit Ethernet 2, gigabit Ethernet 1, gigabit Ethernet 10. This is 0. This is 4. This is 3. This is 1. This is 1. So let me start this up.
But on my routers, those of small gigabit are not showing.
You use this button to turn them on.
Oh, thank you.
When you click on this, it will turn them off and on.
Oh, wow.
So my computer has 2 GB of RAM, so it starts a bit slowly. So when you click this, you see they disappear.
Sure.
So now what I'm going to do, I'm going to create, this is router 1. Let me call it R1. This is router 2. Let me call it R2. This is router 3. Let me call it R3. Now, first understand what I'm going to do. This link is connecting 1 to 2. Okay? This link is connecting 1 to 3. So I'm going to call it link 13. This is going to be link 12, 1 to 2. This is going to be link 23, 2 to 3. Are we together?
Yeah.
This is going to be link 3, only on router 3. This is going to be link 1. So for the rest of the things, they are all going to be 10.0 dot, this is link 12. Are we together?
Yes.
So this one will be 10.0.13.0. And the other one will be 10.0.23.0. This will be 23, it's connecting 2 to 3. This will be 13, it's connecting 1 to 3. This is going to be 12, connecting 1 to 2. And then this one is going to be, who has understood? This one here is going to be 1. It is on router 1 alone. And this one here is going to be
3.
3. It's on router 3 alone. So we have this network. So this PC is on this network. This one is also on this network. This PC is going to be .3. .3, like this, means its IP address is 10.0.3.3. Is that clear?
Yes, John.
Yes?
Yes, John.
Yes, John, it's clear.
So this is going to be .4. Okay? And then on the router, it's going to be .3. Okay, sorry. Let me make this PC 4. Let me make it PC 5 and make this PC 6. Why? Because I want the router to be .3. So this router will be .3 because it is router 3. This will be .5 because it is PC 5. This will be, now don't change things in your topology. I'm only doing this here to make it
understandable.
To make it understandable later on when we are configuring. This is going to be .6 because it is PC6. This is .3 because it is router 3. Even this is going to be .3, but this one will be 10.0.13.3. This will also be .3, making it 10.0.23.3. Are we together?
Yeah.
Yes. So this
Yes,
3
John.
How
will
about
come
that 3?
here and will also be on this interface here. This will be .2, making it 10.0.23.2. This will be .2, making it 10.0.12.2. This will be .1, making it 10.0.13.1. This will be .1, making it 10.0.12.1. This will be .1, making it 10.0.1.1. We are together?
Okay.
Yes.
Now, one of these waiting towards the end of the illustration to say, why is this one .1? All right, this is also going to be .1, and this is also going to be .1. This here is going to be .2, and this will also be .2. I think that's it.
Yes.
So this PC can't be 1, so I'm going to make it PC 3, and I'll make this PC 2 is okay. I'll make this PC 2. It's okay. So this will be .3, and this will be .2. So as we can see, .1 is going to be the default gateway of these two PCs. So this PC is going to be 10.0.1.3 with a subnet mask of 255.255, default gateway of 10.0.1.1. And this PC will be 10.0.1.2. This will be 255.255.255, 10.0.1.1. This PC will be 10.0.3.5, 255.255.255, 10.0.3.3. this PC will be 10.0.3.6. This is going to be 255.255.255.0, 10.0.3.3. All right. So on this router, I need to configure this interface, but right now this PC should be able to ping this one, and this one should be able to ping this one. To understand that, you need to have attended the rest of the classes. Ping 10.0.1.2, we should have a reply because that is one network. Okay.
Yes.
This one should also be able to ping .6.3.6, ping 10.0.3.6. We have reply. If we try to use this to ping this, of course, it will not go through because of this network. So we are going to configure this router and this one, only the interfaces. I'm going to open this router. Where should I put it? Here. And then I will configure its interfaces. Just a moment. I'll first go to system view and change the system name to router 1. Go to interface gigabit and 002 and give it IP address 10.0.1.1. Go to /24. Go to interface gigabit and 00 what? Hold a sec. 00 gigabit 000. Give it the IP address 10.0.13.1/24. Go to interface gigabit and 001. Give it the IP address 10.0.12.1/24. So I can use the display IP interface brief to see that the IP addresses I've given are right. And now I can go to router 2.
John?
Yes.
On interface gigabit 00 on R1, you gave it 13.
Let's go back to R1.
00. Oh, 1. 000 is supposed to be 12.1. All right, thanks. Interface gigabit 000. Undo IP address, and then interface gigabit 001. Undo IP address. So this one, IP address, 1 is 13, 10.0.13.1/24, and then 0 is 12. Display IP interface brief. That's it. All right, thanks. System name is R1, R2 already done. Where is R2? R2 is up there, so let me do this so we can see R2 interfaces. So interface gigabit Ethernet 000, IP address is 10.0.12.2/24. Interface gigabit 002, IP address is 10.0.23.2/24. Display IP interface brief. That's it. So we can go to router 3. System name is router 3. Interface gigabit 000. IP address 10.0.3.3/24. Interface gigabit 001. IP address 10.0.13.3/24. Interface gigabit 002. IP address 10.0.23.3/24. Create display IP interface brief. So 0 is 3.3, 1 is 13.3, and 2 is 23.3. That should be it. So by now, these PCs should be able to ping their default gateway, isn't it?
Yes.
Yes.
So from this PC, I should be able to ping .1.1, and you can see same applies to this PC. I should be able to ping .1.1. That's it. Same applies to this PC. I should be able to ping .1.3.3, ping 10.0.3.3. And from this PC, I should be able to ping the gateway, ping 10.0.3.3. That's it. All right, but now, and even between these routers, I should be able to reach the neighbor. This router should be able to ping this one and ping this one. This one should be able to ping this one and ping this one. This one should be able to ping this one and ping that one. Are we together?
Yes. We are together, John.
Yes, John. So on R1, I should be able to ping 10.0.12.2, and I should be able to ping 10.0.13.3. I use this -C and 1 to specify that send only one packet. I don't have time to wait for all the 5 packets. I have other things to test. So I say, please ping with only one packet, ping this IP address. So it sends one packet. If it's successful, it tells me it's successful. Please continue and do the rest of your things. So I'll go to router 3 and say, ping, but with only one packet, ping 10.0.1.3. Sorry, .13.3.1, excuse me. And you can see the reply came for that one packet. Then I'll say ping, but with only one packet, 10.0.23.2, and the reply came. On router 2, I'll say ping with only one packet, 10.0.12.1, and the reply comes. Then ping, but with only one packet, 10.0.23.3, and the reply comes. So every router can reach every router. But then we have seen this PC can reach this PC, and this router can reach this router, and this router can reach this router, and this router can reach this PC, right?
Yes.
Same applies. This PC can reach this router can reach this router, this router can reach this router, this router can reach this PC. But then, if I ping 10.0.3.5, I won't get replies. Why? Also, if I ping from here to here, I won't get replies. And the issue is, this router can reach this router, but the packet that is reaching this router is telling it to send to this network. Now, this router does not know anything about this network. We can confirm that by displaying, the IP routing table. And we can see that router 1 knows about these networks. 1.0, that is still 1.0, that is still 1.0. 12, it knows only about directly attached what? Networks.
Networks.
It doesn't know networks such as this, which is not directly attached to it, such as this, which is not directly attached to it. It doesn't. Sure. We need to tell it of a way to reach this network and of a way to reach this network. But for now, since no one really needs to go to this network, we can only tell it of a way to reach this network using a static route. But now, carefully watch this. This router can reach this network either by passing network 13, so it can send its packet here, or it can send its packet here. Are we together?
Mm-hmm.
Yes, sir.
Yes. Yes, John.
Now, I don't know, there is that person who has been insisting, that is my problem, that can you unmute yourself?
Yes, John, I'm present.
Yes. Are we together?
Yes, sir.
Don't mute yourself. This is, I don't know who this is. Hossan or what? Whatever
yes,
it is.
Hossan.
Okay. So router 1 can reach network 3 by sending the information 2.3, 13.3, or by sending the information to 12.2. Either way,
Yes.
it can reach. As long as router 2 knows to reach here also. Hosan, is that clear?
Yes, sir, it is clear.
Because router 3 knows how to reach here, it's directly attached. But if router 1 sends to router 2, router 2 also needs to know this because it's not directly attached. So let us first tell router 1 to be sending here. Okay, you tell router 1, hey, in case you want to reach, in case you want to reach 10.0.3.0 with a 24-bit subnet mask, you can send to 10.0.13.3. When we tell it that and display the IP routing table again, you're going to see a new entry. Now it knows how to reach .3 network. Are we together?
Yes.
And it has been learned through static routing. The preference is 60, the cost is 0, and it adds the RD flag. So now, when we ping from here, Hosan, what do we expect? This router knows how to reach there. What do you expect now?
When we ping from here to this router 2, we'll get a reply.
Tell me, Hosan, what do we expect when I run this ping 10.0.3.5? I'm pinging here. This router knows where to send. What do you expect?
We'll get a reply.
We won't get a reply because this router does not know how to talk back. And yet, if we get a reply, it means this one was able to send our reply from here back. But router 3 does not know about display IP routing table. Router 3 does not know about, display IP routing table. Router 3 does not know about the .1 network. You see that, Hosan?
Sure.
And yet, when PC3 says, hello, PC5, PC5 needs to step back. I have had you, PC3. Router 3 needs to know how to send back to network 1. Is that clear?
Yeah.
So we need to tell router 3 also that, hey, in case you want to talk to 10.0.1.0 network, the 24-bit subnet mask, just send to 10.0.13.1. So we have told router 3, display IP routing table. You can see now it knows how to reach network 1. We have told router 3 that in case anyone sends you a packet which is headed to this destination network, this thing that starts with 10.0.1, like this and this, just send to this interface. Now with that, we can just ping here and we really expect a reply. Are we together?
Positive.
Now, notice that that information is not passing up there. You can, okay, I can packet capture. I can packet capture this to show you there is no information going there, but packet capture is going to take our time. I can trace route from here. I can say, can you show me the route that you follow to go to 10.0.3.5? And it will tell you, I first stop at .1.1, which is here. Are we together?
Yeah.
Then I stop at .13.3, which is here. Then I reach where you told me. If I trace route 1,000 times, it will show me exactly the same what? The same traces. Are we together?
Yeah.
We want to tell router 1 that, by the way, you can even pass here. So let me tell router 1 that, wait, human, IP, route static, if you want to go to the 10.0.3.0 network with 24-bit subnet mask, you can actually go to the 10.0.12.2. So when I say display IP routing table again, you look at this carefully, Hosan. You can see, please others mute yourself, only Hosan unmute yourself. you can see that to reach the .3 network, we can pass there. It's been learned through static routing, but we can also pass here. It's been learned through static routing. Are we together?
Yes, John.
But now, as I said earlier, when this router sends the packets for .3.0 to this one also needs to know where to send those packets. Are we together?
Yes, John.
So this one needs to know where to send packets for .3, and for the packets that will come back, it needs to know where to send the packets for .1. Are we together?
Yes, John.
Yes, so we need two static routes in this router. System, IP route. 10.0.1.0 with 24 sent to 10.0.12.1. Then IP route static. 10.0.3.0 with 24 sent to 10.0.23.3. So we've just told this router that in case you get a packet which is going to .3.0, send it to 23.3. But if you get one which is going to 1.0, send it to 12.1. Is that clear?
Yes, John.
So yes, if you display the IP routing table, you will see it knows how to reach the .1 network. It also knows how to reach the .3 network. So now, ladies and gentlemen, let us ping again. This time when we ping, question is, we still get to reach, but where are we passing? Because this router knows two different ways to reach the destination. It knows of this way, sending to 13.3. It even knows of this way. Where are we passing becomes an important question. Let us trace route and see. Did you see where we've passed?
Yes.
Are you seeing where we are passing? We sent to .1.1, then sent to .12.2 here, then sent to .23.3 here, then we reach. Have you seen that?
Yes, John.
When we do it again, that's where we are passing. That's where we are passing. Now, let me trace route again. That's where we are passing. 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 Trace route again. That's where we are passing, and so on and so forth. Now, ladies and gentlemen, I want to capture packets here. Also, I want to capture packets here. So let me transfer.
My head.
Look at this. 1, 2, 3, 4. Do you see this? Time to leave exceeded. Do you see this?
Yes, there is 70.
Time to leave exceeded. I want to show you something very sweet. I'm capturing the packets up from here. I want to capture also the packets down from here. I want to show you something really sweet about network engineering. These are packets from down. So let me ping again. Let me get even the one from up, then ping. I want to ping from here. Look at that. I've stopped this capture. Let me start another one. Sorry, I had paused it. Let me start another one. Here, this is from up. Are we together?
Yes.
Yes, John. Yes, John.
And this is from down. My ping is going to run from here. Trace route. Actually, let me ping. Look at that. Did anyone see that? Did anyone see here? And the reply, sorry, request. Do you see these requests?
Yes.
Yes.
Do you see replies are passing somewhere else?
Yes.
Can you see that?
Yes.
Yeah, the replies are passing somewhere else.
Replies are passing. Because this router does not know of this path. It knows only this one. Are we together?
Yes, John.
Oh, yes.
Although information is going like this, are we together?
Yes, John.
Yes, yes.
Right now, what is happening is ping 10.0.12.2, and I get replies, then ping 10.0.13.3, and I get replies. Now, when I ping from here, am I pinging? Oh, finished. I stopped them already.
I stopped them.
Oh, no, sorry. Excuse me. That will cause more confusion than help. So, but we can see that this router has two parts. Problem is, problem is, it has to be sending packets using two different parts. Display, IP routing table. It has two paths. Now, what a floating route is, we can get this path and put it somewhere. Wait a bit, display IP, routing table, protocol, static. This command runs to show the routes that have been learned by the static routing. And you can see they are here. Now, what I want to do, display current configuration. What I want to do, you see the two routes are here. I want this router to be passing up. No, down is nearer. I want it to be passing down always. It should pass up only if down is not available. Is that clear?
Yes.
Yes. Yes.
So I'm going to go to system view and say undo IP route static 10.0.3.0/24. The next stop, which is 10.0.12.2. I want it to get out. So display current configuration. You see that now I have only one static route that passes on 13.3, which is down. Now I want to put back the one which passes up. I say IP route static 10.0.3.0, the 24-bit subnet must pass via 10.0.12.2. But I want to tell it, trust this guy just a little bit less than the original one. The default preference of static routes is 60. I'm telling it there is actually another path, but trust him a little less, only 70. Because the higher the preference, the little the trust. Are we together?
Yes, John.
So
Yes.
in other words, we are telling this router that display current configuration, we are telling it that always use this one because we trust him. But in case he's not available, then use this one. So look at what's going to happen. Display IP routing table. You can see we have only one route with the down path. The second one is not there. That route is actually in the routing table, display IP routing table, protocol static. You'll see it is actually there. This one is there and this one is there. They are both there, but this one is inactive. Can you see that?
Yes.
This one is active. This one will become active if this one goes off. So engineer Hosan goes with his daughter to work and the daughter plucks out this cable by mistake. Let us try to simulate that. The cable that connects router 1 to router 3, gigabit 001, goes down. Let us take that interface down. System, interface gigabit 001, shut down. It's down. When this interface goes down, okay, let's wait for it to become red, means it's down. When this interface, it's down. When this interface goes down, this router will pull back the static route that was dormant and activate it. Are we together?
Yes, John.
Let us check that on router 1. You see, the moment it reads that the interface has entered the down state, it will pull this route and make it active because this one is no longer available. Let us say display IP routing table protocol static. You will see that there are two routes, but now the active one is the one with preference 70. This one is inactive because its next hop is not available. When we check our routing table, display IP routing table, you will see that the route that exists is the one with the 12.2 next hop. Preference is 70. I trust him less, but I have no other alternative. Are we together?
Yeah.
Yes.
If this interface comes back up, this router will switch to the more trusted path and leave the less trusted path alone. Okay? So when we say undo shut down, and this interface, when it enters the up state, router 1 will also know the interface has gone in up state. When we display this routing table again, this entry will not be here with 12.2. The entry that will be here will be 13.3. Display IP routing table. You see the entry which is there? 13.3. It has automatically adjusted. And when we go to PC3 and you do a trace route, you will see that we are passing down. Can you see that?
Yes, John.
When we shut down this interface, we shall be passing up. Shut it down. Trace route. Excuse me. Trace route. You see, it even loses a packet. Have you seen that? It has lost some packets because it's trying to pass there and the path is not there. Then the router is going to say, wait, I think we can find another path. The moment it finds it, it will switch to the downer path. Now, because this is a simulator, that's not going to happen here. But if it was a real machine, you would see it. For this one, you have to ping again, you trace route again, and then it switches for you the path. Now, this one is happening like this because of the MAC address table. The switch has mapping. You get the idea?
Yes, John.
This switch here has mapping that the packet with this destination should be sent to this MAC address, and there is a mapping here in the table. Are you getting the idea?
John,
yes.
When you trace the load, and you get the stars from the roots. You see the stars only without
Stars
the
mean
IP.
timeout.
What is that timeout?
Stars mean timeout. Stars mean I have reached this guy, but he's not sending anything back. So let us trace route again and see. You see, we need to wait about 5 seconds for it to switch what? To switch path as far as this one is concerned. But the ping will be successful. The ping should be successful, I believe. If it's not, then there could be something that is not right. Okay, so let us display the IP routing table. We have this path with 70. I thought we shut down this path. Ping. Okay. Yeah, I believe it's something to do with MAC addresses. This path is there, and this PC can reach .3.5. Yeah. So when we do trace route, you can see 10.0.3.5. You can see that this PC, this router is still sending there. As I told you, because of the what? Of the MAC address table. We can leave this a bit, and later on, you will see that it will switch to another path. So in this router, we can see that, excuse me, sorry. In this router, we can see that we have an entry to the destination, and on router 3, we have an entry. Oh yes, this is why we are getting timeouts. Okay? This is why we are getting timeout. Sorry. You know, on router 3, we said router 3 only knows of this path, isn't it?
Yeah, I wanted to remind you about that.
It doesn't know of this one. Sorry about that. Doesn't know of this one. So when we ping, right now, the packets are going there. But when this one sends back, this router only knows here and this interface is down, so it will time out. Are we together?
Sure.
So
Yes,
we can tell this router also. That's why you see in this router, there is no destination of .1. It has disappeared. But if we display IP routing table protocol static, it will show that the route is there, but it's inactive because my next hop is not reachable. So we shall tell it that, okay, no problem. Next time you want to reach the 10.0.1.0 network with a 24-bit subnet mask, you can actually send to 10.0.2023.2. So when you display IP routing table again, this router knows, and that should solve our problem. It's not the mapping. Display IP, not display, ping 10.0.3.5, and we can lose a few packets because of the mapping. This is what I had expected at first. You lose a few packets because of the mapping, and then it adjusts automatically. So it has switched the path. And when you do a trace route, you can see that it is passing up. When this interface comes back up, the interface gigabit Ethernet 001, I think. Yes, undo shutdown. When it comes back up and we trace route, you will see that we are passing down. Can you see that?
Yeah.
Yes. Yes, John.
So I think that's it with static route issues.
Thank you.
Thank you.
So this route is what we call the floating static route. Because it is hidden, it is a backup. Like many of you have backup girlfriends. Many girls have backup boyfriends. In case Brian starts fooling around, let me not tell this guy yes or no. Brian might start fooling around and I bring him into the game.
Oh, Jonathan.
Are we together?
Yes.
So this router keeps this one in backup. You do that by manipulating the preference.
By manipulating Brian.
So I think that's it. For the rest of the issues, yes?
Yeah, yes, about the calculations, yesterday we talked about those needs of calculating. How can I effect it there on that diagram?
Calculate what? Calculating what?
Like when you're calculating the path, for example, if they're all having the same
OSPF thingy.
Yes, the same cost and preference values when they're the same.
We said if they are the same, it will load balance.
Mm.
And I already told you that even in this lab, if two routes are here in this table, then it's going to be using that path and this path.
Yeah.
Okay, thank you.
It will be using both.
Break maybe.
Okay, so that is it. We are going to proceed with OSPF after about 15 minutes of a break. Let us together try to appreciate Jonathan for the great work done. He has answered almost, actually not almost, all the questions. I only stopped him with this one because he was copying for you, actually.
Actually, Jonathan, it was really good.
Yes.
Plus also
Yes,
Johnny
Jonathan is a great guy. Sometimes I get stuck on what to teach next and I ask him and he helps me out almost immediately. So thank you, Jonathan, for the great work. I only came in on this particular lab because I felt like we are copying for these guys and they are some of them are recording their screens. So I decided we have a completely different break, different topology so that we can have that. So let's have a break and we shall come back with and proceed from exactly where we stopped in OSPF. Today, I'll explain the necessity for the designated router and backup designated router, the problems of exchanging too many packets, making our networks very busy, and I'll explain in detail the working mechanism of OSPF. If you're lucky enough, we shall also have a small OSPF lab to make the matters rather simpler for you to understand. So 35, 1035.
Because of route summarization loops and how they can be achieved.
Yes, we are going to talk about that before the end of today's class.
All right.
Don't forget. So 10:35, 15 minutes, 10:50, we return for OSPF.
All right.
Okay, John.
I know now some of you are going to start saying, John, I can't hear you. John, I can't hear you. So for those of you who are there, when you hear those guys, tell them we are returning at 10:50 after the break.
Right.
Bonify, you had an issue with error 40. I've also managed to solve mine, but I had to first disable the virtualization from BIOS. Then I restarted my PC without it being enabled. Then I went and I ran ENSP. The devices were starting after like disabling virtualization. Then I turned off the PC, then I re-enabled virtualization. Then I restarted the PC again. Then it worked. You first try that and see.
Boa. Allah ta gina shi da kabin wasa masu mai zai su tabbatar da
Hello, good morning, Mr. John. I hear you.
We are in a break.
Welcome back. Welcome back.
Welcome back, John.
Thank you.
Welcome back, John.
So as usual, this session is being shared on a live stream on YouTube. So you can actually find it at where? I'm providing the link in the chat just in case someone gets stranded in the group because of the number. I've put the link for the stream in the chat. At about midday, I will share the link to today's attendance. For now, let us start from exactly where we stopped yesterday with OSPF. I think we've had enough breaks. Actually, not enough, too much break. So we had, we talked about the basic concepts and OSPF packet types. And after talking about OSPF packet types, I mentioned that we have three main entries or databases in OSPF, three main tables that OSPF needs to maintain. The first table is a neighbor table. Every time you have a router that has a certain router ID and another router, and they form an OSPF relationship, they are going to be neighbors. They can be neighbors. Neighbors can stop at neighborhood, or they can go up to what we call adjacency. We shall see the difference between this. So there are two kinds of neighbor relationships, or two kinds of relationships in OSPF. Neighbor relationships and adjacency relationships. You are going to see the difference between those. When you run the command display OSPF peer, you're going to be shown.
You're not showing your screen, John.
You're going to be shown the neighbors that the router you ran display OSPF peer on. Its neighbors will be shown to you when you run the command display OSPF peer. Are we together?
Yes. Yes, John.
Yes, we are together now.
So when you have two routers and they form So when you have two routers and they form OSPF relationship, you can use the command display OSPF peer to see the neighbor table. And as you can see in this illustration, we have such information. It will tell you the router ID, the address, the interface to which that neighbor is connected, who is the designated router. We are going, what's the maximum transmission unit, and other information. As you can see here, we shall see all this information. So the OSPF neighbor table really contains much key information like router IDs, interface addresses of neighboring devices, and other information. The other table in OSPF is the link state database table. When OSPF relationships are found between any two devices, we said they will exchange their link state advertisements, and so they will have a unified link state database. This link state database is another table that OSPF players need to maintain, and you can always run the command display OSPF link state database in order to see that table. So as I've mentioned, table number one is the neighbor table, and it displays the neighbor information in OSPF. We have two kinds of neighborships in OSPF. The neighborship we call neighborship, and the neighborship we call adjacency. Those are the two kinds of neighbors we have in OSPF. You use the command display OSPF peer to see this first table that OSPF players, routers that run OSPF are called OSPF players. So OSPF players need to maintain that table. The second table that OSPF players need to maintain is the link state database table. We said step one in forming an OSPF, in OSPF operation, step one is neighbor discovery. After discovering neighbors, what you do is to exchange link state adverts. When you exchange link state adverts and they are now equal, it means your link state database is unified or synchronized. That link state database needs to be maintained by each of the routers in the same area. To display the link state database of OSPF players, you will use the command display OSPF LSDB, link state database. The third table that OSPF players need to maintain is the OSPF routing table. Now, please note, the OSPF routing table is a table specific to OSPF. It's a routing table that lists all routes that have been learned through OSPF. Note that for the link state database table, there are a number of fields that are important. The type field, the advertising router field, as you can see here, the link state identifier, the advertising router, the age, the length, the sequence, the metric, the type. There are many types of link state adverts outside coverage of this particular level. For OSPF routing table, we have seen routing tables, I'm sure, which is the general tool that any router uses to find directions to different destination networks. Now, these routers learn these routing tables in different ways. Either the route is directly attached, or it has been statically configured by the network administrator, or it has been learned by a dynamic routing protocol such as OSPF, such as ISIS, such as BGP, such as READ, such as EIGRP, and so on. So for OSPF, the routes learned through OSPF will have OSPF under the protocol field in the routing table. These routes are also there in the OSPF routing table. So what exactly happens in OSPF is that every OSPF player maintains all the routes learned through OSPF in the OSPF routing table. Now, some of those routes, this is now very important for you who plan on upgrading your skill set of network engineering. Some of these routes will be taken into the routing information base, the local RIB. The local RIB is the local routing table that we check when we display the command, when we run the command display IP routing table. We are seeing the local one. That one shows the directly connected, the static connect, the statically configured, the dynamically learned through OSPF, through ISIS, through BGP. It has all of them, but not exactly all of them. It has all the optimal routes. So every protocol has its own table that maintains all the routes learned by that protocol. But then there is the local routing information base that maintains all the optimal routes. Maybe route network N1 was learned through OSPF, and route network N1 was learned through static routing, and route network N1 was learned through ISIS. Now, ISIS preference is 15, or static routing preference is 60, OSPF preference is 10. Assuming none of the defaults has been changed, this one will be extracted from the OSPF routing table and inserted into the local routing table, the local routing information base. So to display the OSPF routing table, you run the command display OSPF routing. So this brings us to the general end of the OSPF overview. And now we are going to dive into the working mechanism of OSPF to understand what exactly happens in OSPF behind the scenes. How does it do what it needs to do? And how does it achieve the goal of routing to the final destination? How is OSPF very capable of implementing scalability? How is it capable of being scalable, being implemented on enterprise networks from small scale, medium scale, large scale, and so on? How is OSPF capable of doing all these things? We are going to look at how it establishes neighbor relationships. How does it know this is my neighbor, this is my neighbor? What is the role of the router ID, the priority, and other things all under the working mechanism of OSPF. So first, let us try to examine the relationships between different OSPF routers. So when I have a router here and another router here, and they are connected, and I have configured OSPF on router 1, I've configured OSPF on router 2, these two routers are going to form a relationship. One important thing you need to know about OSPF is the two kinds of relationships. One of those two kinds of relationships is called a neighbor relationship, excuse me. Okay? Neighbor relationship. Normally, when you go to a new homestead, you choose this house. Someone stays there, someone else stays there, someone else stays here, someone else stays there, someone else. For some people, you will know them and other details about them. For some people, you only know that he's John and he stays in house number 2. That's all. You don't need to know the rest of the information. That one is just your neighbor. For others, they are probably your buddies, as people call them. So OSPF has just neighbors, and it also has buddies that we call adjacencies. For some of the players, an OSPF router forms an adjacent relationship with the player. So OSPF has two kinds of relationships: the neighbor relationship and the adjacency relationship. It's imperative that you master these two kinds of relationships and which one means what. Later on, we shall explain why each of them is very important. Basically, when this router finishes determining that there is another router that also uses OSPF, once they finish establishing that, the two routers are neighbors. They have set up a neighbor relationship. Now, later on, these routers, depending on which router is what is the role of the router in the OSPF protocol? Depending on the role of the router, we have talked about the fact that sometimes router 1 and router 2 exchange link state request, exchange link state update, exchange link state acknowledgement until the link state database of router 1 is exactly equal to the link state database of router 2. This procedure, ladies and gentlemen, moves us to the relationship we call an adjacency. What are we trying to say? An OSPF player will be in a neighbor relationship with others and in an adjacency relationship with others. Are we together at that point?
Yes, John, we are together.
Yes, John.
So if this is an OSPF router, this is another OSPF router, and this is another OSPF router, and they are all connected to the same switch, it means they are in the same OSPF network. This is router 1, this is router 2, and this is router 3. You might find that router 1 and router 2 form an adjacency. Router 1 and router 3 form an adjacency. But router 2 and router 3 only stop at neighborship. This is important for you to understand. So all through this working mechanism, we are going to try and understand for which routers do we stop at neighborship, for which routers do we stop at adjacency. It's important to note that you can only become adjacencies if you manage to successfully pass through the neighborship. So let us look at the process of establishing an adjacency relationship. In this case, we have router 1 and router 2. And we say these routers will first need to establish a neighbor relationship between themselves. This router will send some kind of packet that will later on call a hello packet, and this one will also send a hello packet. When they both receive hello packets with the other neighbor's ID in his packet, then they have formed a neighbor relationship. That's all. They are now neighbors. After being neighbors, they want to negotiate who is going to be the master, who is going to be the slave. Now, the purpose of this negotiation is a very simple objective. We want to determine who talks first? Who is going to talk first? It has nothing to do with who is the boss and who is the servant. No, it is just in case we need to talk, who talks first? Whoever will be talking first will be the master, and whoever will be talking last will be the slave. That's the purpose of that relationship. So step number one, establish neighborship, which is the first relationship type. Step number two, determine the master-slave status of the two players. Step number three, you want to exchange a linked state database summary information. Later on, we shall see that we use the packets we call the database descriptors to exchange the summary information. After exchanging the summary information, we start these three packets: link state request, link state update, link state acknowledgement. We exchange these until the link state database of 1 is exactly equal to the link state database of 2. Once this is achieved, we have now reached an adjacency. And when we are at adjacency level, each router will independently calculate routes. Are we together? You should note that router 1 does step 1 on its own, step 2 on its own, step 3 on its own, step 4, sorry, not on its own. Step 1, 2, 3, and 4, step 1, 2, 3, and 4 are done together. You need to interact in order to perform those steps. Interact in order to perform those steps. Interact in order. You need to interact between 1 and 2. For step 5, router 1 performs independently, and step 5, router 2 performs independently. So now, we are going to examine these steps. What exactly happens in each step? Are we together?
Yes, John.
Yes, yes. Right. So let us look at the first step. For the first step, now you should remember, we talked about 5 OSPF packets. We say the first one is the hello packet. Who remembers? The second one, we say, is the database descriptor. Database descriptor packets. The third one, we say is the link state request. The fourth one, we say is the link state update. The fifth one, we say is the link state acknowledgement. Now, the hello packet is the one we exchange to form in the first step to form neighborship, which is the first type of relationship. And how exactly does this happen? We say every router has a router ID. Now, forgive us, this is not an area, this is router ID, okay? Every router has a router ID. So this router is router 1.1.1.1, this router is router 2.2.2.2. When the router 1, when you enable OSPF on router 1 on interface, let us say 0/0/0, this interface starts sending out hello packets. Says, hello, I am 1.1.1.1. I'm not sure who you are, but I'm told you also speak OSPF. Now, when a router receives a hello packet from another router, and that hello packet, as you can see, does not contain the recipient's router ID. Is that clear?
Yes, John.
The router that has received goes into the init state. Now, of course, around the same time, this router will also send a what? A hello packet that does not contain the router ID of router 1 to take this one to init. Please note, you change state because you have received a packet, not because you have sent. Is that clear?
Yes. Yes, John.
It is interesting how some people are focused on attendance link than the lesson itself. That's rather interesting.
You know, we are there.
So, when this router 2 receives a hello packet without its own ID, it goes to init state. When a router receives a hello packet that contains its own router ID, you see in this case, router 1 has received a hello packet from router 2, but that packet contains router 1's router ID. How did it get it? Because router 1 told it that this is my ID. So when you receive that packet, you go to two-way. In the same way, when router 2 receives another packet with router 2's router ID, it goes to two-way. So when you're at two-way state, your neighbors. So first state is down. From down, you go to init. From init, you go to two-way. You go to init because you've received a packet that contains your neighbor's router ID without your own router ID. You go to two-way because you've received a packet that contains your neighbor's router ID and your own router ID. You become neighbors. After becoming neighbors, we have said we shall go to step number 2. In step number 2, we are going to negotiate who is the master and who is the slave. So in step number 2, we are negotiating who is the master and who is the slave. This happens in the extract and part exchange stage. So after forming a neighbor relationship in the two-way stage, you go to extract. In the extract state, your neighbor sends a database descriptor assuming he's the master. Each router assumes is the master at the beginning. This one is also assuming is the master. But ultimately, we need only one master and we need only one slave. Question becomes, how do we choose who is the master? Whoever has a bigger router ID becomes the master. In your heart, repeat after me. Whoever has a bigger router ID becomes the master. So at the beginning, router 1 will say, hey, I'm going to be the boss. So every time you speak, we shall start at X, and this is my router ID. No, write it somewhere. At the same time, router 2 is saying, hey, I'm going to be the boss. Every time you are going to speak, we shall start at Y. Please note down my router ID. Each of them assumes they are the boss. The rule of the protocol is whoever has a larger router ID becomes the boss. So whereas router 2 had router 1 say, hey, I'm the boss, and router 1 had router 2 say, hey, I'm the boss, router 2 will silently compare his own router ID with router 1's router ID, and we'll see that his router ID is bigger. In the same way, router 1 will compare his own router ID with router 2's router ID, and we'll see that router 2 is bigger. At that state, router 1 will admit and say, okay, I agree. We shall be speaking beginning from Y. Is that clear? Y was a number set by 2. And because 2 has a larger router ID, 1 will adjust to that sequence number. So 1 will say, also, this is the summary of my link state database. This one will also send a summary of the link state database, of course, incrementing the sequence number as the rules of TCP/IP, and then of TCP, sorry. And then once we confirm these database descriptors have been sent bidirectionally sent in the exchange phase, we now know the contents of router 2, and router 2 knows the contents of router 1. That is the second step. Now we know that router 2 is the master. Why? Because he has a larger router ID. We know that router 1 is the slave. Why? Because he has a smaller router ID. Then we shall proceed to step 4. Now, please note that this here, we have talked about step 3 and step 2. Step 2 is to determine master and slave, which is just after these 2 extract. Then step 3 is exchanging the database descriptor or link state advert summaries. That is step 3. We have exchanged the link state advert summaries, and now he has the summary of my link state database. I have the summary of his link state database. So step 2 and step 3 are all done. Then we go to step 4. In step 4, you see, after getting the summary of router 2's link state database of router 2 says, I have link 1, this and this and this. I have link 2, this and this and this. I have link 3, this and this and this. I have link 4, this and this and this. I have link 5, this and this and this. I have link 6, this and this and this. And this side, we have got the link state database summary of router 1. Says I have link 1, this and this and this, link A. I have link B, this and this and this. I have link C, this and this and this. I have link D, this and this. These are just summaries. Now, inside router 1, he already knew about link 1 and link 4 and link 5, but did not know about link 2 and link 3 and link 6. On the side of router 2, he knew about link A and D, but he did not know about link C and B. In that case, router 1 will ask router 2 to send details of link 2 and link 3 and link 6. He asks that through a link state request. Are we together?
Yeah.
Yes.
In the same way, router 2 will ask router 1 to send more information about the links he doesn't know about, the details. He will ask that through link state request. So we shall send a link state request, and then the router will send back a link state update. Oh, this is the updated information about that link. Every time we receive an update, we send an acknowledgement for that update. So in the same way, router 1 sends us a link state request. We send a link state update. He sends us a link state acknowledgement. Does that make sense?
Yeah.
This process continues until the entire links of router 2 are known to router 1, and the entire links of router 1 are known to router 2. At that stage, ladies and gentlemen, the link state database of router 1 is exactly the same as the link state database of router 2. And once that is done, we go to the final step 5 of calculating our routing table independently, or our routes independently. Is that clear?
Yeah.
Good. So for the neighbor table, you can see it contains the area in which the OSPF neighbor is. Are we together?
Mm-hmm.
Yes, John.
Sorry. This is the ID. Okay, this is the area in which the OSPF neighborship has been formed. Then the ID of the neighbor, the ID of the router itself is here. We are running display OSPF peer on router 1. It will show router 1's ID from there. Somewhere it will show the ID of the neighbor and the IP address of the interface to which this neighbor is connected. Sorry, to which this neighbor connects to us. Does that make sense?
Mm.
The interface on us and its IP address that connects to the neighbor is shown there. The interface on the neighbor is not shown because we can't know it, but the IP address of the neighbor that connects to us is shown there. The designated router and the backup designated router will be indicated. The state, you can see, is full. The state full means we have formed an adjacency with them. The state two-way means we have formed a neighborship with them. So the total states, 1 is down, 2 is init, 3 is two-way, 4 is extat, 5 is exchange, 6 is loading, and 7 is full. Are we together?
Yeah.
Now, I want you to understand that these 2 steps are of significance in OSPF. These 2 are known as stable states. So these others are transitional. We only pass through them. Are we together?
Yeah.
But these 2 are stable. In other words, router 1 and router 2 can be in 2-way when they are operating their OSPF in 2-way state. Or router 1 and router 2 can be in full state when they are operating their OSPF in full state. Is that clear?
Yeah.
Yes, but they cannot be in extat. They are operating in extat. If you check your OSPF and you see the state stopped at extat, there is an error you need to solve. Are we together?
Sure.
If you see it stopped in exchange, there is an error you need to solve. If you see it stopped in init, there is an error. It means it has not received the hello packet that contains its own ID. Now, there is another step we normally hide here called attempt, but this one is on non-broadcast networks, which happens when we know our neighbor, but the neighbor has not yet talked to us. So those are the stable states, 2-way and full. In this case, when you see full, it means we have gone up to the last stable state. OSPF supports 4 types of networks. And these are not networks of WAN and LAN, and so they are OSPF network types. Okay? When 2 routers form an OSPF relationship like this, there is some kind of network between them. This network is going to be either a broadcast network or it's going to be a non-broadcast multiple access network, or it is going to be a point to multi-point network, or even a point-to-point network. So a broadcast network, when you see network type is broadcast, or non-broadcast multiple access, or point to multi-point, or point-to-point, it means the OSPF network is that one that has been indicated. Are we together?
Sure.
Let us talk about these networks a little bit. The first network is point-to-point. So an OSPF network type can be changed manually to point-to-point. You can go to this interface and say OSPF network type point-to-point. And then you go to this one, you say OSPF network type point-to-point. You can do that manually. But also, if you connected 2 devices using a serial link, okay, the default layer 2 protocol that will exist between them is point-to-point protocol. As such, when you enable OSPF here and enable OSPF here, the relationship, then the OSPF type, network type, will be point-to-point. Are we together?
Yeah.
So point-to-point is the default network type of OSPF if we connect 2 OSPF players through serial link. If we connect players through Ethernet, that one we have been using for most of our labs, the default OSPF network type is going to be broadcast. Is that clear?
Yeah.
They don't have to be connected through a switch. Even if it is router 1 to router 2 connected through gigabit Ethernet 0/0/0 and gigabit 0/0/1. When you enable OSPF here and enable OSPF here, by default, this link is going to be broadcast. Network type. Are we together?
Yeah.
Okay.
Yes, John.
I hope we are together.
Yes, John.
The third network type is non-broadcast multiple access. Non-broadcast multiple access, it means that different network devices can access different network devices, but they don't support broadcast transmission. We have talked about broadcast. There is nothing like I'm alone, but I want to talk to many. No, it can't happen. Although you can share the network, one frame cannot be sent to many receivers. Is that clear?
Yes, I find it, sir.
It is non-broadcast. I hope that is clear.
Okay.
Yes.
Yeah.
A typical example is the frame relay network. Then we have point to multi-point network. In this case, you can see a single point is connected to point 1 and point 2. One point connected to multiple points in that kind of setup. This is called a point to multi-point OSPF network. Now, there's one thing I need you to understand. There is no network or layer 2 technology link that if you set it up between two devices, the default OSPF network is point to multi-point. Is that clear?
Yes.
We have said if you connect two OSPF players through serial links, the default OSPF network is going to be
point.
If you connect two OSPF players through an Ethernet link, Ethernet, gigabit Ethernet, 10 gigabit Ethernet, and so on, the default OSPF network type is going to be
broadcast.
Access.
If you connect OSPF players through a frame relay network, the default OSPF network is going to be
a non-broadcast.
Non-broadcast multiple access. There is none. You see, frame relay is a layer 2 technology. Ethernet is a layer 2 technology. Yes. Serial is the one that gives us point-to-point protocol. Is a layer 2 technology. So for different layer 2 technologies, they are default OSPF network types. Do you understand that?
Yeah.
But for the fourth OSPF network type, there is no layer 2 technology that by default leads to point to multi-point network type. Are we together?
Sure.
Point to multi-point network type is always a modification of another network type. So you can have a full mesh, a non-full mesh, non-broadcast multiple access network, and you manually change it to point to multi-point. You can have two different point-to-point links. You have point-to-point and point-to-point here through frame relay, and you manually configure it into point to multi-point. Are we together?
Yeah.
But you don't have a default point to multi-point. Anyways, there are four network types. The first one is broadcast network, typical of Ethernet networks. The second one is point-to-point networks, typical of point-to-point protocol links. Third one is non-broadcast multiple access, typical of frame relay links. The fourth one is point to multi-point, typical of modification. Are we together?
Yes, John.
Yes.
Good. Now let's talk about something interesting. Yes?
Yes, John. I have a small question.
Is it small?
Yeah, could you please shed more light on frame relay?
No. That is very old. It is like asking me to shed more light on ATM. Frame relay is no longer a technology we teach in DATACOM because it is a very old technology. So shedding more light means you want me to explain how it works and other things, but that is out of this, not in scope of this class, completely not examinable, and you're not going to find any new network set up these days using frame relay. So that would be kind of spending efforts for no good reason.
Okay, thank you, sir. Thank you.
Frame relay knowledge might be helpful for those people who will find legacy networks and might need to maintain them, and they had been built through frame relay. But most of the networks have moved to Ethernet, point-to-point over Ethernet. Okay? So yes, it is there, and we need to talk about it a bit like that, but we haven't removed it from our contents. But it's a layer 2 technology, like PPP, like Ethernet, data link layer protocol. But you can read a little bit more about it. If you read a little bit more and get confused, you can inbox me to explain. I will explain. If I explain in this class, it's going to be a little bit a wastage of time.
Okay, John, thank you.
Yes. So, OSPF networks that support broadcasts are broadcast multiple access and non-broadcast multiple access. They support multiple access. Okay. Now, on multiple access networks, such as broadcast multiple access and non-broadcast multiple access, each router needs, notice, ladies and gentlemen, I need you to be very carefully following at this state. Are we together?
Yeah.
Are we together?
Yes, we
have reached. I need you to follow with me very carefully. We earlier said OSPF routers will begin from the downy state. Then they will go to the init state. Then they will go to the two-way state. At this stage, they are neighbors. But remember, we also said for router 1 and router 2 and router 3 and router 4 and router 5 to calculate routes, they need to exchange link state requests, link state updates, link state acknowledgements. Yes?
Yeah.
Now imagine we want the link state database of 1 to be equal to the link state database of 2, to be equal to the link state database of 5, to be equal to the link state database of 4, to be equal to the link state database of 3. What does that mean? It means 1 needs to exchange link state request, link state update, link state acknowledgement with the 2, link state request, link state update, link state acknowledgement with the 5, link state request, link state update, link state acknowledgement with the 4, link state request, link state update, link state acknowledgement with the 3. Are we together?
Yes.
In the same way, router 2, in the same way, router 2 needs to exchange link state request, link state acknowledgement, link state update with router 1, exchange link state request, link state acknowledgement with router 3, link state request with router 4, link state with router. Are we following?
Yes.
In the same way, router 3 needs to exchange link state. You can see, I'm even having trouble speaking it. What about them that actually have to do it? You get the idea?
Sure.
Yes.
Exchange link state request, link state update, link state acknowledgement with this one. Exchange link state request, link state update with this one. Exchange link state request, link state update, link state acknowledgement with this one. In the same way, router 4 needs to exchange link state request, link state update, link state acknowledgement with that. Link state request, link state update, link state request, link state request. In the same way, router 5
What are you
need
saying?
to exchange link state request, link state update, link state acknowledgement with 2, link state request, link state update, link state acknowledgement with 3, link state request, link state update, link state update with 3, with 4.
Hello?
This is just with 5 what? Routers. Are you getting the problem?
Sure.
Yes.
This is too much traffic on our network, excluding my ping as the administrator. Do you see that?
Sure.
Too much. Too much. And big enterprises have 100 routers, 1,000 routers in the same network. If we have to exchange this for 1,000 routers, the network is going to be very, very busy. So, router 1 needs to form a relationship with that. That's one relationship. A relationship with that, 2 relationships. A relationship with that, 3 relationship adjacencies. A relationship with that, 4 relationships. Then a relationship between this and that, 5 relationships. This and this, 6 relationships. Are we together?
Yeah.
This and this, 7 relationships. Are we together?
Yes.
This and this, 8 relationships. This needs to form a relationship with this, 9 relationships. This needs to form a relationship with this, 10 relationships. This with this, 11 relationships. Which one else?
On 2.
2 to which one?
2 to 1.
1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3.
25.
1, 2, 3. This one needs to form with which one? 1, 2, 3, 4. I think that's it. I think there is a relationship I've not numbered, but there are 12 relationships.
Yes.
No, there are actually 10 relationships. There are 10 relationships. Okay? There will be 10 relationships. There is a formula to find the number of relationships. The formula is n into n minus 1 over 2. N is the number of players. So in this case, we have 5 players. We shall have 5 into 5 minus 1 over 2, which is 20 over 2. We shall have 10 adjacencies to form. If we have 10 routers, we shall have 10 into 10 minus 1 over 2, which is 45 relationships to form. Too much nonsense on our network. Do we all see that?
Yeah.
And what is the objective of these relationships? Having the same what?
The same database.
The same database. Is there another way of doing that?
But John,
through a
Hello, John.
central router somewhere.
Hello, John.
There is another way of doing that. You know?
Excuse me, John.
Yes, please.
What if they are on different area? Are they still going to maintain the same adjacency and be sending that nonsense all over the network?
No. But if we have different areas and each area has 6 routers, that is already 15 relationships in each area. If each area has 10 routers, that is already how many relationships? 45 relationships in each area. That is too much exchange. That is too much exchange. Now, there is a way, if all these routers are connected in an OSPF process, okay? What we want is router 1, router 2, router 3, router 4, router 5 link state databases to be the same. Are we following?
Yeah.
Yes.
Why can't we elect router 2? So everyone sends their link state database to router 2. Are we together?
Yeah.
Yes.
Now, router 2 can share his database with everyone. Haven't we achieved the objective?
Yes, yes.
Have we reduced the number of relationships?
Positive.
Yes. Perfect.
John, can you explain that a bit? I think
There is nothing to explain. Guys, these things are not difficult. You're only thinking of them as difficult. The objective of exchanging link state request, link state update, link state acknowledgement is so that we have the same link state database.
Sure.
We are saying instead of one sending his to 2, then 1 to 3, then 1 to 4, then 1 to 5, then again 2 to 3, then 2 to 4, then 2 to 5, then again 3 to 1, then 3 to 4, then 3, then again. Why can't we get 1 to share with the 2? Then 3 also shares with the 2. Then 4 also shares with the 2. Then 5 also shares with the 2. Don't we have the same link state database on 2 now?
Yeah.
Yes.
Everything achieved with very few packets exchanged. Are we together?
So
yeah.
Yes. So John.
Yes.
So how do we call that router there?
Slow down, man. Slow down. Please slow down.
Okay.
Have you understood first?
Yes, I have.
So this tool that we are electing is our leader. We are choosing two to be our area, chairman. Everyone shares their secrets with the chairman. The chairman can discuss with the rest of the people instead of everyone sharing with everyone. Unfortunately, in OSPF, we have no chairman. What we call the chairman in OSPF is the designated router. Are we together?
Yo.
So we want to elect a designated router in our OSPF network to help us reduce on how many packets are exchanged. Is that clear? We are electing a designated router. How do we elect the designated router? We use a special number called the designated router priority. Every router has a special number called DR priority. If your DR priority is the biggest, you will be the DR. Are we together?
Sure.
Every router has a special number on it. The moment you enable OSPF, it gets a special number called the DR priority. After, when they all activate OSPF and they know we are 5, we are all speaking OSPF, they will all compare their DR priority at interface, 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 their DR priority at, as you can see. And whoever has the biggest DR priority will become the designated router. Like in our example, router 1, router 2, router 3, router 4, router 5. Everyone has a DR priority. So who will be the designated router in this case?
Or maybe the one who goes on first. I don't know.
We have the designated router priority and it is on the black screen. I'm asking who will be the designated router?
5.
Whoever has the highest, guys go with me. Whoever has the highest designated router priority will be the designated router. From 1, 2, 3, 4, and 5, who will be the designated router?
But they all have the same
all
thing.
have one.
That's the problem. Sometimes the DR priority of 1 is the same as the DR priority of 2, is the same as the DR priority of 3, or just even 2.
I have a suggestion.
Wait a bit. So now we have another problem. The rule is, if you have a large DR priority, you become the DR. But wait, we have the same DR priority. What happens? In that case, ladies and gentlemen, we go back and look at your router ID. Whoever has a big router ID becomes the what?
Designated.
Are we together?
Router. Sure.
We look at the router ID only and only if some players have tied the DR priority. DR priority is at interface level. The interface on which OSPF is enabled has a DR priority. If that router and that router have the same DR priority, we shall look at their router IDs. Whoever has a larger ID becomes the designated router. Again, the role of the designated router is to be the boss. And by being the boss, he's helping us reduce on the amount of packet exchange in the bid to synchronize the link state database. Are we together?
Yeah.
Yes.
Good. Now let me show you something interesting. We have router 1 here, router 2 here, router 3 here, router 4 here, router 5 here. And OSPF designers have been too sharp. Instead of exchanging too many packets, they have actually decided that router 1 has router ID 1.1.1.1, router 2 has router ID 2.2.2.2, router 3 has router ID, 5.5.5.5, router 4 has 4.4.4.4, router 3 has 3.3.3.3. Designated router at the interface of router 3 is, designated router priority is 1, 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 designated router priority is 1. When they compare to choose, because they don't want to exchange too many packets and make our network busy, they choose a designated router. However, when they compare the designated router priority, they see it is the same. So they need to choose something else. They look at the router ID. They find, so who is the designated router in our network?
5.
So they elect this one as the designated router. When they finish electing that one as the designated router, router 2 shares his link state database, router 1 shares his link state database, router 3 shares his link state database, and router 4 shares his link state database. Once they have all shared their link state database, as you would expect, router 5 will now share the same database with each of them. So we all have exactly the same what? The same thing. Are we together?
Sure.
Now there is a problem. What happens, ladies and gentlemen, when router 5 is sick?
We repeat the other process.
We start electing again.
Yes.
And we have the same problem we are trying to avoid.
Of failure?
No. Too much exchange of packets.
But now we are going to elect router 4.
Why can't they also elect the
router 4? We have to exchange again. So
I think backup and master.
I think all of them they are in converge already.
That we call single point of failure. We don't elect only the designated router, but we elect the designated router and also elect his vice that we call the backup designated router. At the same time, if the designated router fails, the backup is already there. Are we together?
Yeah.
Yes.
What does this tell you? In an OSPF network, we have a router called the designated router. We have a router called a backup designated router. What about the others? Because those others do not have DR on them, we call them DR others. This is their name. We have 3 types of OSPF routers in an OSPF game. We have the designated router, we have the backup designated router, and we have DR others. And they are called exactly as I've said it, DR others.
Others.
Are we together?
Ego.
What I want you to master is what relationship, because we have 2 types of what?
Of relationships.
We have neighbor relationships and
adjacency.
Adjacency.
What I need you to master is which relationship is formed between a DR and BDR. Which relationship is formed between a DR and DR other? Which relationship is formed between a BDR and DR other? This is one word, by the way. Which relationship is formed between a DR other and a DR other? These are 4. I need you to know them. The relationship formed between a BDR and a DR is an adjacency relationship. The relationship formed between a DR and DR other is an adjacency relationship. The relationship formed between a BDR and the DR other is an adjacency relationship. And the relationship formed between a DR other and a DR other is a neighbor relationship. Why is DR other and DR other stopping at neighbor? Is because they don't need to exchange link state request, link state update, link state arc. They are exchanging these ones with a DR and BDR. Is that clear?
Okay.
Yes.
So for them, they can only stop at neighborship. Is that clear?
Yeah.
Good. I hate it when I'm explaining something very important and someone is asking for their attendance. It feels to me like some people are joining the class to fill attendance and go away. It is disgusting. And in fact, I'm going to keep looking at this name, Destiny Kabote and Abu Baker. I want to see how long they are going to be in this class. Let me expand my list here so I can be seeing them up to the end. Because I wonder how something very important to engineering on a very important protocol is being explained, and you have the energy to ask for the attendance link. So let me be looking at these people, and this one called the student. Let me look at them and see how long they are going to attend this class, because I've not been seeing their names from the beginning. They pop in to ask for the link, and when it does, they go off. Now they are waiting to post in the chat. My network went off before filling in attendance, but I have been around for the entire session. Guys, let us try to be in class. So that is DR and BDR. I have explained this thoroughly well. Okay. I've said the interface with the highest OSPF DR priority will become the DR. Unfortunately, the DR priority of OSPF is 1 by default. So unless you change it, all the routers will have the same DR priority. In that case, the routers will choose a router with a larger router ID to become the designated router. One important thing is that BDR election happens in non-preemption mode. What preemption means is that you are the president, I am your vice. What happens when you fall sick? I become the president. Where preemption or non-preemption comes in, what happens when the president recovers? Are you with me?
Yeah.
Does he take over immediately and become the president? Or does he wait for 2 months for the vice president to finalize, then he takes over presidency again? Are we together?
He takes it.
If he takes over immediately, that protocol is operating in preemption mode. The moment I come back is the moment I take back my chair, period. You have helped me, that is very good, but now I'm back. Are we together?
Yeah.
Yes,
what we call non-preemption means that you were the president, no problem. I was the vice. You felt very sick, and because I need to help you, I temporarily became the president. It is true you have recovered, but for now I'm the president. So you be the vice, or if you want, or be a normal citizen of the country. I'm the president. Do you understand?
Yeah.
Yes.
That is non-preemption. So OSPF works in non-preemption. Let us say this designated router has priority of 100. This one has priority of 50. These ones have priority of 1. So this one became designated router, this one backup. But for some reasons, this guy gets a problem. Maybe this link has been plucked out. This one will become DR immediately. Then you come back and plug back in the link. It is true your priority is greater than mine, but you went off, my dear. I am now the boss. In fact, we have elected another backup. When you wake up, you will be a DR other. Are we together?
Oh, yeah.
That is what non-preemption means. If something happens to this network and we have to elect afresh, you will take over as a DR. Are we together?
Sure.
Because your priority is high, but if you went off, you have disappointed our what? Our trust. The fact that you've woken up, we won't give you back the chair. Be a DR other. You can walk on the roads of dust with no one to be on your convoy and feel how it feels. When we elect again, no problem, your priority will take over. That kind of operation is called non-what? Non-preemption. Is that clear?
Yes, sir.
Perfect.
Yes, John.
Sorry, can you write
let us-
the spelling
let
of
us
non-preemption
briefly-
or whatever you call it?
Pardon?
I said, can you please spell out the non-preemption or what do you call it?
What do I call it?
I think he's talking about the spelling for
The
preemption.
spelling.
What is the spelling for pre?
Preemption.
What is the spelling for emption?
EMPTION.
So which spelling do you want?
Thank you. I've seen it.
Preemption.
Need to know.
Emption
I just wanted to be sure.
Okay?
Yes,
You
wanted to be
empty
sure.
your role. So there is no emptying my role. Please note that preemption and preemption come when you want to take back your seat. Are we together?
All right.
So
John, I have a question.
I already told you, OSPF works in single area for other small enterprise networks and in multiple area for larger enterprise networks. So in single area mode, an OSPF area can range from 0 up to 255, and it is normally expressed by the protocol in this format. So it can range from that up to that. But it is important to note that if you're working with single area OSPF, the area number can be any supported number, 0 all the way to 255. Are we together?
Yeah.
But if you're working in multiple area OSPF, 1, there must be area 0. Are we together?
Yeah.
You can't say I have area 10 and 4 and 6. For me, they are the ones I want. There is nothing like they are the ones you want. There must be area 0. Choose the others, but 0 is a must. Number 2, all other areas must touch area 0. Is that clear?
Mm-hmm.
The reason for this is outside scope for this class. But I'll explain in details for those of you who passed this one successfully and joined my professional level class. Why? We shall even illustrate why, if you don't touch area 0, your network is messed up. Are we together?
Okay.
Yes.
But for now, just know, if you have area 1, 0, and 2, 1 and 2 must touch 0. Is that clear?
Okay.
Yes.
You can't put area 3 here. It must touch
Area
0.
0.
Are we together?
Yeah.
Yes, John.
Good. When you're working with multiple area OSPF, number 1, you must have area 0. It's a must. It's called the core. Are we together?
Yeah.
Number 2, you must have all other areas to touch area 0. In fact, we have had cases of troubleshooting networks like these ones, where someone set up area 3 there, and we are forced to create a virtual link between area 1 to touch area 3 to make it believe that it is touching area 0. Without that, the network will have problems. Again, why that has to be like that is a bit outside scope for this class. But for now, you should know that the core reason for that is to prevent what we call inter-area loops. Keep that at the back of your mind. How, why, and the details are outside scope of this class. All right?
Yeah.
Now, as you can see, we have a router that is in between area 1 and area 0. We have a router that is in between area 2 and area 0. We have routers that are only in area 2. We have routers that are only in area 0. We have routers that are only in area 1. That brings the concept of 4 types of OSPF routers. The first type, forget those ones of DR, BDR, and DR other. Those ones are also there, 3 types. But now, there are 4 types of OSPF routers for multi-area OSPF. The 4 types are area border router, like that one and this one. Are we together?
Yeah.
Internal router, like this one, and this one, and this one, and this one, and this one. Are we together?
Yes.
And even this one, and this one, and this one. Are we together?
Yes.
Yes.
Routers that have all their interfaces in the same area are called internal routers. They are internal to that area. Routers that have some interfaces in another area and other interfaces in another area are called area border routers. Are we together?
Yes.
Listen carefully.
Sorry, John.
Routers that are internal routers, but they are in the backbone area, area 0, are called backbone routers. Are we together?
Yes, Afani.
Yes.
Internal routers in area 0 are backbone routers. Now I know the sharp ones of you are saying, aha, John, today we have you. You've finished the internal routers. You've finished the area border routers. You've finished the backbone routers. Now what is the fourth type? Hold a sec. If this is one autonomous system, like Stanbic Bank, like MTN, like Renault, excuse me, and others, sometimes Renault needs to connect to MTN to exchange routes. Are we together? Sometimes MTN needs to connect to Airtel to exchange routes for interworking of certain services. Are we together?
Yeah.
Yes.
So there is an entire autonomous system with its areas for Airtel, internal routers, backbone routers, area border routers for Airtel. But a certain router in MTN needs to connect to a certain router in Airtel so that Airtel routes can be brought into MTN. MTN routes can be sent into Airtel. Is that clear?
Yeah.
This router that connects an autonomous system to the outside world is a border router of the autonomous system. So it's called the autonomous system boundary router. It is the fourth type. Are we clear?
Yes, sir.
Yeah.
Perfect. And those are the 4 OSPF
John.
routers. The internal router,
John.
area border router, backbone router, autonomous system boundary router. Yes, please.
Yes, John, I have a question about the backbone.
Those are 4 seconds wasted. By the time you call me, I know you have a question.
Yes.
Hey,
And that's
now
the question,
repeating
like
that statement is wastage of time. Just ask the question.
Like I need some more light about the backbone router. I think my mind had skipped there.
Now, how do I know now your mind is stable?
It is stable because it is.
How do I know?
Because I'm asking the question.
Tell me about the area border router so I know you're stable.
Okay, the area border router, that's the one which is between the area 2 and the area 0, or area 1 and area 0. The router
What
that
if
connects
it is between area 4 and area 5? What, now your network is bad. What if it is between area 4 and area 5?
I'm not seeing the network there, so in others, I'm lost there.
Use the interface.
You said something earlier that you. Are you with me, John?
This is area 5. A router is here. Now you can see. So is it an area border router, an internal router, or what?
Area border.
Yes.
It's area border router still.
Area border router still. Now someone is saying autonomous system boundary router.
No. Out of context. Sorry.
Now I want to listen to me very carefully. Are you hearing? Are you all listening?
Yeah.
Yes, sir.
You said any non-zero area.
Yes.
Must touch area 0.
0. Yes.
Are we together?
Yes.
As such, if a router intersects two non-zero areas, it doesn't qualify to be an area border router. Is that clear?
Yes, positive.
Because routes from this area can't go through that router. Routes can only enter area 0 or get out of area 0. They can't go from area 3 to area 4 and back. They can't. Are we together?
Yes.
Good. Now, for your answer, I said an internal router like this one. These ones are internal routers, yes?
Yes.
But these are special routers. Why? They are internal in the core area.
Oh, yeah.
Are we together?
Yes.
You see, if you were Ugandan, you have a father, isn't it?
Yes.
Even Museveni's children have a what?
A father.
If you are married and you're a man, you have a what? A wife. Even Museveni has a what?
A wife.
But Museveni's wife is the first what?
Lady.
He's a president, ladies and gentlemen. But the first lady is just a what?
A Wi-Fi.
What are we saying? This is an internal router. No problem. Okay? This is also an internal router. No problem. But hey, this router here is in the boss area. It needs to have a special name. Are we together?
Sure.
So it is a backbone router. Just like Museveni's wife is a first lady and his family is a first family, as if for us we don't have families. Even if your family came before his will be the first family. So that is it. That is it. Let me complete this very quickly. Typical OSPF single area configuration. You can see here, you have a few players. This is a single area. And here we have multiple area. You can see area 0 at the aggregation point and core. And you can see area 1 being at the aggregation connecting to core. And then area 2 also aggregation connecting to core. Area 0 in core. So you can see 0 is connected to 1. It's also connected to 2. So if routes need to go from 1 to 2, they need to pass through 0. Are we together?
Yeah.
Routes can't go direct from 1 to 2. By that, we prevent loops. OSPF configuration, this one I'm just going to show you commands. We have done the labs already. And as you can see, you can say OSPF and you specify the process ID. Sometimes you even specify the router ID, or you can specify a router ID from system view. Then when you get into the OSPF view, you specify an area, area 0, area 1, area 2, and so on. Then when you get into the area, you enable OSPF RT interfaces. Yes, I know many people have told you, you advertise networks into OSPF. I'm saying you enable OSPF at interfaces. When you run the command network 10.0.12.0.0.0.255, what you're doing is to enable OSPF on interfaces that are in that area. This command is enabling OSPF. It's not really advertising anything. It's only saying if an IP address lies in this area, enable OSPF on the interface where that IP address has been put. That's why we use a wildcard mask and not a subnet mask. You can set the OSPF cost at interface point using OSPF cost and you specify the cost. We talked about the bandwidth reference, which we say by default is 100 megabits per second. You can manipulate it if you want OSPF to have more realistic costs for your interfaces using the bandwidth reference command and specifying a value. you can use the OSPF designated router priority command at interface level to specify the designated router priority, which ranges from 0 to 255. Now listen to this. If the designated router priority of a certain router at a certain interface is set to 0, that router does not participate in DR or BDR election. Is that clear?
Yeah.
Perfect. This is a configuration example. You can try this out in your own time. And other configuration examples, we have labs we have done. You can add these to the labs you have done. You can always run some few display commands to verify what you have configured. Any question?
Sorry, John, I have a question. Let the other guy go ahead first.
Pardon?
Okay, my question is the router ID.
John, I'm asking.
It be anything?
Pardon?
I mean, the router ID, can it be any number? It should just be in form of IP address, like IPv4
It can be any number between 0 and 255. And yes, it is written in form of an IP address by the same.
All right, thank you very much.
Welcome.
Please mute some people.
Another question?
My question is from lab 9. In lab 9, we were told to identify that there's the designated router. And I wanted to know which command really should be used to identify which router is the
that is copying. You know, really, you want me now, we tell you the command. Now for you, what will you do?
We shall type the command.
You tell me, for you, what will you do?
Type the command.
We have talked about several commands here, and we have seen the information those commands show you. Did you see no command showing DR somewhere? You want us to tell you that go and use this command?
This.
Yeah? No. That one I don't do. Apologies.
All right.
Like you want me to tell you, you use this command. Now for you, what will you do? Just go and type it in. Yeah? We have taught, and if you've been following, I've gone through the different display commands here, and we have seen what they show you in this material. It's a matter of reserving some time to reflect what we have learned and try out a few things in your ENSP, and boom, you'll have what you want. Now you want someone to tell you the command is display joined while teaching. You will see the DR. Then you go and type it and see the DR.
John, shall we sit exams for labs?
No.
Okay.
I know now you are happy, but yes,
not really.
No, you won't.
Hello, John. Mine is a request.
Yes.
For only today's session, I will suggesting if it's possible to share the recording, because some of us had missed the first part. We joined in the second part.
I know now some of you already know the answer to that one.
Okay. Yeah, you know the answer.
I'm sure some of you now, some of you have been able to learn a bit of me during this class already. And you know the answer to that one.
And then the other thing, I have a suggestion.
Let him ask why we're laughing.
That other thing, I think you can go ahead, yes?
The last topology where you're talking about a static route, I have a suggestion I would like to give. Yeah, we're talking about static routes and we were configuring the floating route. If it is okay, allow me.
Allow you to do what?
I have a suggestion on that static route where you were configuring that topology which had 3 routers.
Which had 2 routers?
It had 3 routers, 3 routers.
Yes.
I have a suggestion. If you could share the screen, I could do, say it out while you're sharing the screen.
Share which screen?
The one having that topology for
I
static.
closed the ENSP and did not save the topology and deleted, even uninstalled ENSP. I install it when I have something to illustrate.
Okay, let me just illustrate. I can just illustrate from here.
You can just ask the question or suggest what you want to suggest.
Okay.
At least I remember the topology.
Okay, remember those routers, there was router 1 and also router 3.
Yes.
They were connecting to that networks where we had the end devices.
Yes.
So my suggestion was, if we are configuring that other floating route and we want us to allow to have that automatic switching in case one interface is down. So I'm suggesting we should configure that floating route on both routers, on router 1 and router 3. That if any of the interfaces in those networks connecting them is down, you could have automatic switching, because at first I saw we only configured it on the first router. That's my suggestion. Hope they can get it.
But I think after we configured it on the second router also.
The second router, I saw as if we configured just a normal static route, we didn't configure a floating route, unless I missed.
Yeah, we didn't configure the floating route.
Yeah, so
yes,
my suggestion
we configured the normal route.
Yeah, suggestion was we could configure a floating route to have automatic switching and flexible switching.
Now, one thing you guys should understand in these classes is that we look at unidirectional. Chances are the router on the other side is not yours and you don't know where they want
in the
their
lab
traffic
you
to pass.
expected to
Do you understand?
Yeah.
Chances are the router on your side, you know where your traffic you want it to pass. You don't know where the traffic of the other side they want it to pass. Do you get the idea?
Yeah.
Yes, we do the labs for you to understand the technicality. So if you're the one this side, you know what to do. If you're the one the other side, you will know what to do. Are you getting the idea?
Mm-hmm. Yes.
I don't know whether you get, I mean, for our lab, what you're suggesting is valid. For the enterprise, the scenario is normally different. You're configuring your network, not your ISP's network. Do you understand?
Yes.
So the ISP knows how he has configured their floating static route, whether they are using OSPF or IA, it's up to them. For me, on my side, I want the traffic to switch here if this one goes down.
Okay.
The ISP might be, are you getting what I'm trying to show you?
Yeah.
So the other side of router 3 is someone else. Router 1 is ours. And we are telling it how to reach the .3 network. I don't know whether it makes any sense. But for our lab, since it is our lab, yes, your suggestion is perfect and it makes sense. But for real application, you will normally have different players in the network. Chances are it is not entirely your network.
John, if at all we are getting the network from the ISP, do we assume the priority or we ask in case it's an enterprise?
You can see my screen, right?
Yes.
I've had this confusion in several classes. This is normally what is happening. This is your router at the egress. It is normally a router. For some enterprises, it's even a firewall. Your entire network is here. You understand? You have maybe some switches here, aggregation switches, maybe 3 connecting there, maybe one aggregation switch connecting to access switches, connecting to, you have maybe OSPF running here, maybe what, do you understand?
Yes.
This is your entire enterprise. This router is to nut your traffic out to the internet. Now, you've decided to pay both MTN and the Airtel, because you know it is not possible for MTN network to be up 100%. Sometimes it will go down. Do you get me?
Yes.
Now, you come and set this as the primary route and set this as a floating what? Route. Are you getting me?
Yes.
As you can see, in the actual scenario, there is no need for this one to switch to that one because MTN does not work with Airtel. The other one is a completely different path. Do you understand?
Yes.
So there is nothing like you configure a floating route even here. No, this is your network, not the other one. I don't know that you're getting it.
Yes.
Yeah. Me, no, not yet. There is a.
When you configure this one with the preference 70, it means you're deciding to normally use MTN. If MTN fails, you will use Airtel. Now, there is nothing like MTN also needs to have a floating route there. MTN has its own floating routes. It's up to him. For me, when the link between me and MTN fails for some reason, I'll use this one. That's it. Do you get it?
Yeah.
Yes.
That's why for most of the things, we are normally going to focus on traffic 2. For all those labs you have probably seen. The only reason we are configuring this one sometimes is so that it can talk back to us. Not because configuring traffic from this side is our job, no. Do you understand?
Yes.
It is for our ping to be successful, that's all. But chances normally are the network this side is not your network and it has nothing to do with you. All you want to do is your traffic to go out and out in load balancing or in active standby mode. So you set the preference of this to 70. So we'll be passing here. If we fail, we shall pass there. Now, whether these people also have that they pass here, if they fail, that is up to them. Maybe for them, they even have a connection to the internet that can still connect them. That is up to them. For our labs, we are configuring this router so that our ping can come back. That's all. Are we together?
Yes.
Yes.
Yes, I hope you understand.
Yes, it's now very okay.
So that brings us to the end of OSPF. Now, please notice that beginning tomorrow, you will notice some kind of shift in my speed. If you get completely troubled by that shift, I will ask you to be open enough to let me know. But by now, we have covered most of the essentials. We are now going to be talking, okay, we have layer 2, it's very essential also. We are going to start on layer 2 tomorrow. But you'll notice I might cover 2 or 3 chapters beginning tomorrow. Again, it's because you now know the general mapping of how traffic is moving on our network. I'll keep hinting on some of the advanced concepts, but we are not going to be at this slow pace forever. Now you see this guy, Jacob King. You have just joined the class and asking someone to post the attendance so that you can feel it. So let me post the attendance now, and I'm going to watch people feeling, and I'm going to delete those ones who have joined less than 15 minutes from now. I'm going to manually delete them. The attendance is there, you can feel it. I'm going to manually delete people who have just joined now to feel. We have 15 minutes to close class. You join to fill the attendance and leave. That's not going to work. So the link is there. You can go ahead and fill
It's bringing errors.
At that point, it is telling you to refresh your browser page and fill.
By the way, John.
Yes.
Yes, this is just a round of applause to you. Thanks for the lessons. Truly, at least I'm getting some good image about communication of these things. I've been hearing them, I've been knowing them, but I don't know how they do communicate.
Me too, I also
At
found
least
they
now
are
I
very
can,
difficult.
because now I'm just seeing everything. It's like some nice magic. The other time it was too magical. But at least now I see everything working out. Thank you.
Sure.
All right,
Excuse
you're
me,
welcome.
John. I have a question.
Yes.
So
John,
what
I
if
beg, no mistake, delete me. I've been in this group for a while. Right from the beginning of
what if
Someone is asking, I've just muted everyone, please ask now.
yes, sir, I was asking a question. What if someone wants to create his own like ISP service and then wants to connect to another ISP? Will that, like, how will that happen so that the networks can communicate?
Depends on how you want to connect to another ISP and depends on what ISP service you're creating. Some ISP services are small services that are providing ISP services that other ISPs are providing them. Does that make sense?
Could you please break it down a bit?
I've already broken it down a lot.
Where?
So you are in Uganda, you're staying in Kampala, you buy MTN internet, MTN is an ISP, and you start distributing it around your local area. So you've become an ISP, isn't it?
Yes.
But you're already MTN's client. So now connect to who?
But then let's say in your local area, right? MTN is not there. MTN doesn't provide to your local area. Reason
but
why?
You are MTN.
Pardon? Hello?
I'm saying,
yes, sir.
If I am giving you my internet, this is where I stop. Okay? You come and pick it from here.
Yes.
You pay for a month.
Okay.
And then you have radios that beam it to an island where I'm not working.
Yes.
This is MTN, isn't it?
Then screen.
We are not seeing the screen.
Hey, you open your eyes widely. Can you see it now?
Yes, yes, positive.
Yes, we can.
I'm saying this is MTN. It does not cross its network up to there. But not crossing networks simply means they don't have masks on that side, isn't it?
Yes.
So you buy MTN dedicated internet. You have studied network engineering. You get some radios, put them on poles, and beam this internet to an island where MTN is not working. Yes?
Yes.
But we know that this is MTN internet, isn't it?
Yes.
Hey, so now you want to connect with who? Because you are MTN. Do you get me?
Oh, okay.
You are MTN, so you're connecting with who? You don't control this internet. It is MTN's internet.
Oh.
When MTN disconnects you off, you don't know how it is reaching you. Maybe the person you claim you're connecting to is the person giving MTN. What do you know?
Okay.
Are you getting the picture?
Yes, now it's...
So at a rather advanced level, we shall talk about autonomous system numbers. These ISPs get AS numbers from Afrinic if you're in Africa. Maybe they have 3369, maybe 77614, maybe, I know it doesn't reach this far, maybe 47614, maybe 51512, maybe different autonomous system numbers. When traffic is moving at advanced levels, we shall not be speaking routers. We shall be speaking autonomous system number 1, autonomous system number 2, autonomous system number 3. Now we have what we call BGP peering. When you are an independent ISP like NITA, you need to connect with MTN through peering your autonomous systems. You'll set up a peer connection between NITA's autonomous system and MTN's autonomous system. So NITA will advertise its routes to MTN, and MTN will advertise its routes to NITA. Now, everyone in MTN's autonomous system can reach everyone in NITA's autonomous system. Do you understand?
Yes.
But now, if you're just a client of NITA, it doesn't matter whether you've taken NITA's internet to India, you're just in that autonomous system of NITA. Do you understand?
Yes.
Yeah.
So you can't peer with another autonomous system because it is not your autonomous system. You don't have control over it.
Okay.
It is like I have my router and the network is 192.168.4.6. I've connected it to a switch. I have 24 users, so my switch is full. Now you have your PC here, but you realize you've done some network engineering and you want to give also your brothers and sisters, so you put a switch. Are you getting me?
Yes.
This switch is still distributing my IP pool, isn't it? You can't have your own network of 192.168, maybe .19. something. No. Now you need your own router. Now, if you need your own router, it means you need to configure NAT. Because me, I'm giving you only one IP address here. Do you understand?
Yes.
The thing is, you are in my network. So that's why I said ISP of which level. If you mean small ISP giving a small network, you're really not an ISP. You need to be in good relations with your master ISP. You tell them what you want to do. If you're a master ISP, you'll set up what we call BGP peering, and you'll set them up on permission with the ones you want to peer with. And in most cases, they will send you people to check your autonomous system for BGP attacks like prefix hijacks. For BGP is a very vulnerable protocol. It doesn't have good security configured in it. So there are some agreements, there are some concessions BGP users through ISPs are agreeing on using. Again, most of this stuff is beyond scope of this class. So I hope your question has been answered.
Yes, thank you.
Welcome. All right, so I'm giving you extra 5 minutes for your own time. Feel free to use them what you want. I'm closing this class now. Be reminded that I never give my time for free. So in one of the classes, I will make sure I will use extra time, at least 50 minutes. I normally multiply by 10, sorry. So I use the time well to do what you want to do. I have extended all the quizzes that have been enabled so far. They are all available up to Sunday. And I have made their attempts unlimited. Please note,
thank you, John.
if you don't
Thank you so
reach
much.
the final quiz you need to reach, you will not do my exam. I know you want them unlimited, that you do one quiz for 7 years, but you should know that every next quiz is harder than the previous one. Because I'm making questions from the previous quizzes dynamic, they will be changing. If you decide to take your time, the way I see by the look of your names, you prefer taking your time. I don't know whether you'll be able to finish the quizzes in time. I encourage you to do as many of them as you can. Otherwise, use your 5 minutes well. We are at the end of today's session. Thanks for attending. We shall continue the chat in the chat.